Another sample problem. So here it says the figure shows a circuit with elements who have foreign values E1, E2, R1, R2. Okay. Yeah, so E1 is here, E2 is here and here. Okay, so actually it's three battery here. Yeah, but only two different values. Okay, so and then R1, we have R1 here, R1 here. R1 also here, so three R1s. And then actually this is also R1. So altogether 4 R1s and 1 R2. Okay, so actually we have 5 resistor and 3 battery. 3 battery. So actually we don't have any idea what is the direction of the current. What is the direction of the current? Okay, so here let us try to use the mesh analysis. Let us try to use the mesh analysis. Yeah, actually, if we really use node analysis, how much voltage we need to assume? Okay, for this circuit there are quite many nodes. Okay, for example, this one is an independent voltage. This is dependent. Okay, so this is 0. This will be E2, but this is another independent. So this is another one, and then this is a 3. Okay, so if we need to use node analysis, we need to assume 3 independent variable. Okay, this one, and this one. Okay, these two nodes are dependent to each other. These two are dependent to each other. These two are dependent to each other. Yeah, if they are dependent to each other, you can consider this is a node, and then this is a node, and then this is a node. Okay, something like this. So altogether we have 4 nodes, and then one is the ground. So we need 3 variables if we really use node analysis. So here we try to use the mesh analysis because clearly we can see we only need 2 mesh. Let's say this is I1, this is I2. Okay, I just use I2 following the direction of I2 here. Okay. Of course, you can still define I2 to be clockwise, okay, just ignoring the direction of I2 here. Yeah, but here we will just show it like this, okay. So it doesn't really matter even you assume the current to be clockwise or counterclockwise, okay. If it is a negative value, that means the assumption should be reversed, okay. Okay, so for the mesh one, okay, we start from let us start from here. Okay, let us start from here. So here we are going up. So here we have E1 and then equals this one are going down. So we put on the opposite side. So we have I1, R1, R1, I1, R1, I1. And then going to here, okay, this one will be I1 plus I2, okay. I1 like this, clockwise, I2 counterclockwise like this. So for this branch, it should be I1 plus I2 for this branch. So I1 plus I2 times R2. And then this is going down. This is high, this is low, so this is plus E2, okay, but opposite side to the E1, so here we have a plus sign. Yeah, if you are not familiar with it, you can just put a E1 minus this term minus this term minus this term equals 0. Yeah. Okay, so here we can slightly rearrange the term. So here we have a E1 minus E2 equals okay, so this is let me see, this is I1. I forgot, here we still have another R1, so here we have a plus I1 R1, okay, plus I1 R1. Okay, so altogether we have a 2 R1 I1, and then plus R2, okay, I1. Okay, we all together have this I1, and I1. Okay, so all together 2R1 plus R2 are all multiplied by R1. And then plus R2, I2. Okay, so this will be the first equation. And then for mesh 2, okay, so let us start from here. Okay, so here this is and then going counterclockwise. Okay, or maybe you start from here going counterclockwise. So this is R1 I2. R1 I2. We just put it on the other side, and then this is going up, so we put it on the left side. And then for this one, I2 R2 plus I2 R1. It should be I2 R1 for this resistor. And then for this one, plus R2 times I1 plus I2. And then here going down, so plus E2. Okay, so here we can slightly simplify it. We can actually cancel this E2 and E2. So we have this is I1. Okay, so here we have a 0 equals R2 I1, and then plus, okay, this is R2 R1 R1. Okay, so we have a 2R1 plus R2 I2. Okay, so this is the second equation. So we have a two equation with two unknowns, and then we can also substitute the values. Okay, so E1 minus E2 is 3 minus 6 equals R2 is 4. 4 times 2 times 2 plus 4 I1, and then plus 4 I2. And then for the second one, this is 0 equals R1 I2 is this is R2 I1 is 4 I1 plus 2 R1. Okay, 2 times 2 plus 4 I2. Okay, so these two turns out to be 8 I1 plus 4 I2 equals -3, and then 4 I1 plus 4 I2 equals 0. So yeah, based on your junior school mathematics knowledge, you can be able to solve it to be I1 to be negative 0.58, and then I2 to be 0.258. Yeah, so so we know I1 and I2, and also I3 in between. I3 in between will be I1 plus I2, that is 0.5, negative 0.5 plus 0.25, which is negative 0.258. Okay, so any questions? So actually it just asks you to find the current. Okay, I ask you to find the current. Okay, so which means that I1 is negative 0.5, which means I1 should be from right to left, from right to left. I2 to 0.25, yeah, also from right to left. And then for I3, okay, this is negative, so it should be from bottom to top, from bottom to top. Okay, so yeah, so here we slightly talk about the ammeter and voltmeter. So simply speaking, the ammeter is used to measure the current. Yeah, but here we have some concern here. Okay, so we have some concern here for the ammeter in this figure. Okay, so original circuit is like we have a circuit like this. Originally, the circuit will be like this is E, this is R. Okay, so this is a practical EMF, and then okay, so this is R2, this is R1. So originally the circuit is like this. The original circuit is like this. Here we would like to measure the voltage. Okay, let's say here V1. And also we would like to measure the current going through this single loop. Or maybe I just wrong. Measure the current and the voltage across the R1. So in that case, we would like to have this ammeter in series with the loop. We would like to measure. Okay, so actually for the ammeter, it will have a resistance RA, the internal resistance RA. So the resistance RA should be very small, much smaller than the other resistance in the circuit. Okay, because yeah, so here it is like you are connecting RA here like this. Okay, if RA is large, okay, let's say if it is as large as R, and then the total current will be induced, will be inference. So let's say this is I prime, this is I. Okay, so originally if we try to find I based on this circuit, this I will be E over R1 plus R2 plus small r. Okay, like this. Okay, but first we just try to ignore the voltmeter at this moment. So in that case, this I prime will be like E over R1 plus R2 plus small r plus RA. Okay, if this RA is not small enough, okay, it will reduce the current, and actually it will. The RA can never be zero. So we at least hope this RA is much smaller than all the other resistance. In that case, it won't influence too much. OK， 就是这个电流表的话，它的内电阻 RA 的话，应该要远小于其他的电阻不然的话会影响到整个电路的电流当然它肯定会影响，但是所以这个 RA 应该是越小越好。Okay, so now we try to consider this V. Okay, we try to consider this V and just ignore the ammeter there. So this is the voltmeter. So simply speaking, the voltmeter is used to measure the potential difference between any two nodes. Okay, so for the resistance, okay, so it also has an internal resistance. But for the voltmeter, we would like to hope the voltmeter to have a much larger resistance than all the other elements in the circuit. Yeah, because here we have RV. Okay, so here we just ignore the RA. So in that case, V1. Okay, so this is V1 we would like to measure. Okay, the V1 we would like to measure. Originally, based on this circuit, V1 will be like will be like E times R1 plus R2 plus R, and then here we multiply by R1, okay? It will be like that. It will be like that. But here is the V1 prime in this circuit will be like E is still E, and then we have R1 parallel RV, and then R1 parallel RV, and then plus R2 plus R. Okay, so the difference is like this is R1 here. This will be R1 plus RV. This one will be R1 parallel RV. R1 parallel RV. And then if you still remember the parallel equation is like R1 parallel RV will be like R1 times RV and then R1 plus RV. Okay, here if RV is very large, it will be like R1 and then over R1 plus RV plus 1. Okay, so this is, yeah, we don't make any approximation yet. We just divide RV on the top and on the bottom. So if RV is very large, the first term will goes to 0. R1 over RV, if RV is very large, RV is very large, then it will be approximately R1. Okay, so yeah, so 就是说并联电阻的话，肯定会比两个最小的那个还要小。但是如果另外一个是无穷大的话，那并联之后就会跟原来小的那个一样。就是反正并联之后电阻会越来越小的。那你要保持着那个电阻的话，那你就只能够把另外一个加得很大。Okay, so in summary, okay, so the ammeter measure the current and the voltmeter measure the voltage. So the internal resistance for the ammeter should be very small compared to the other resistance, and then for the internal resistance for the voltmeter should be much larger than the resistance, other resistance in the circuit. Okay, so this is a quick summary. Okay, so here comes the RC circuit. RC circuit, just similar to the RL circuit in chapter 30. Okay, so yeah, so here we have a RC in series, and then at the beginning, okay, for T is smaller than 0, the switch is connected to the ground, so which means we will have an initial condition to be like this is VC. Okay, VC T should be equals to 0 when T is smaller than 0. Okay, so this is the initial condition we have. Okay, so when T equals 0, the switch going up to the position A, then finally it tells you that the current I will be like this, and then the VC will be like this. So here we would like to simply derive. So here we have the E, and then we have the R, and then we have the C. This is VC, and then also we have VCT equals 0 when T is smaller than 0. Okay. So the initial condition VC 0 plus should be VC 0 minus. As I mentioned before, the voltage across the capacitor should be continuous. So after the switch is closed, the voltage across the capacitor should still continuous. So it should be equal to 0 volt. Okay, so here I. Okay, so we would like to use the KVL here. So E. Okay, we start from this node and then we are going up. Okay, okay, this is going up, so E equals, this side will going down. Okay, for this resistor, R times I, V equals IR, and then plus, okay, for this one is actually VC. Okay, but here we have two different function. Okay, what other function we have? What other equation we have? So the answer is I equals C dVc dt, as I mentioned before. Okay, so we need to make use of this one. If you forget how does it come from? Okay, so we have a Q equals CV, and then you take the derivative on both sides. You have I equals C dVc dt. Okay, so here we have this one. We can plug in this expression to here. So it turns out to be RC dVc dt plus VC. Okay, so we have a dVc dt plus 1 over RC VC equals E over RC. Okay, so this is a constant coefficient linear first order ODE. So for first of all, we would like to solve for the homogeneous equation. So the first derivative change to S, and then plus 1 over RC, and then the original function turns to 1, okay, equals 0. So S equals negative 1 over RC, or we can just call it negative 1 over tau C, okay, which means tau C is defined to be, tau C is RC, just as this one, okay, or here only tau. Okay, so yeah, like this. So which means the VC complementary part will be A times exponential to negative T over tau C or RC. Okay, so this is the time constant for the RC circuit. Last time for the time constant for the RL circuit will be L over R. So this time RC. Okay, so this is the complementary solution, and then the VCP, the particular solution for this one. Okay, this is a zero order polynomial. So we just assume this is also another constant. So we just plug in this one into here. Okay, so for the first derivative of a constant is 0, and then plus 1 over RC times B to be E over RC. So which means E equals B. Okay, and then what? And then we have I mean B equals E. Okay, so in that case, VCT will be VCC A times exponential to negative T over tau C, and then plus E. Okay, so this is the complete solution, but we still have this initial condition. So which means VC0 plus will be, we plug in T to be 0, so this is A plus E to be 0, which means A to be negative E. So it turns out VCT to be E, and then 1 minus exponential to negative T over tau C. Okay, so this is VC. Okay, so this is actually this one. Okay, this is 2735 VC. So how about I? I is nothing but C dVc dt. So for the C, okay, so take the derivative. Okay, the first one is a constant. Okay, and then we have a negative E times small e to the negative T over tau C. And then for the chain rule, we still have another negative 1 over tau c is RC. Okay, so we just put it out. Okay, so finally we can cancel this C and this C. Okay, and then we have a 2 negative side. So it turns out to be E over R and then exponential to negative T over tau C. Tau C. E over R exponential to negative T over RC or negative T over RC. Okay, so this is I. So here this is I. E over R times exponential to negative T over RC or tau. Okay, tau C. It's the capacitive time constant. Yeah. So yeah. Let me see. Okay. So yeah, we already finished the derivation. So so the next stage is to discharge the capacitor. So which means just now we already ended when we take t to be very large. When t tends to infinity, this I will be a 0. This I will be a 0. And then this Vc will be E when it is fully charged. This term will become 0. So Vc will be E when t is very large. So which means in this case, we have the initial condition Vc t to be E when t is smaller than 0, something like this. This is the initial condition. And then here, the switch goes from position A to position B. So it start to discharge， 就是它会放电。刚才这个情况是充电，就是这个的话就是 VC 会这个是 Q 的 VC 吧，因为它有一个叫 Q 等于 CV 的东西嘛，也就是说 C 是一个常数 ，Q 跟 V 是成正比的，所以这个是 Q 的话 ，VC 也是有一个同样的形状，它就是这样充电，充电的过程，它的电压就会升高到 E 为止如果是 VC 这个轴的话，那这里一点就是 E 充电。那你切回去，从 A 切回到 B， 就是这个开关从 A 切回到 B 的话，那它又开始放电，它就开始这样放电。那放电的话，就是会像会这样，可能会这样放电。然后我们把这个拉回到 t 等于0，在这个 case 里面它就会这样放电那为什么这么放電的話，我們也可以推導。So let's see. Here we don't have a battery. We only have a resistor and a capacitor in series. Okay, and then the circuit is simply like this. And then this is VC. This is I. Okay, so here we don't have the E. Okay, so we only have a 0 for the battery part. And then we have a R times C dVc dt. Okay, so this part is the I. And then we plus Vc. Okay, so yeah, so we start from here. Okay, plus 0 equals this part R times I is C dVc dt. Okay, so the current direction is like this. So this is plus, this is minus, going down and then going down again. So Vc. Okay, so we have a RC dVc dt plus RC to be 0. Okay, so here we have a dVc dt and then plus 1 over RC. Vc equals 0. So similarly, Vc to be A exponential to negative T over RC, okay, just as what we have previously. And then according to the initial condition, VCT to be E when t is smaller than 0. So this is the initial condition. So VC0 plus E equals VC0 minus to be E. And then in that case, substituting t to here, we will get A. So A equals E, which means VC of t should be E exponential to negative t over RC. Okay, so this is the expression for this one. Okay, or V0 or V0. Okay, so charge up to V0. So maybe we can just change, this one to be V0. This one to be V0, and then this one to be V0, and then also this one to be V0. So like this. So here we have already derived this one, and then for this one is easy. I equals C dVc dt. dt, okay. So C dVc is like V0 exponential to negative t over RC, and then the chain rule will be like negative 1 over RC. Okay, so here we can cancel this C and this C. Okay, so finally it turns out to be negative V0 over R, and then exponential to negative t over RC, like this. Okay, so this is actually this one. So without knowledge of the solving the constant coefficient linear ODE, you may not be able to understand why the so-called the transient response will be like this. Okay, we will call it transient response in circuit theory. 中文叫做站态响应，站态响应。态响应，态响应 ，transient response。但它最终稳定的话，它就会变成一个常数啊，变成一个没有变化的东西。但是它中间它会有一个充电或者说放电，它会有一个慢慢变化的过程。OK